In the last video, we took a further look at motion under uniform acceleration. And now it's natural to make a pivot to start to think about what it is that causes objects to accelerate. And that turns out to be forces. Now, forces are one of those things that we've already got a half-decent intuitive understanding of. So we'll start there, and then we will refine it and make it more precise. So intuitively, we can think of a force as just being a push or a pull on an object. And if we think about it a little further, we realize that force has to be a vector quantity, which means it has both a magnitude and a direction. Right? If we go and say throw a ball, how hard I throw the ball is going to determine how fast it ultimately goes. And which way I throw the ball is ultimately going to determine which way it flies. So our throwing action, which would be a push on the object, has both a magnitude and a direction. So it makes sense to try to treat this as a vector quantity. There we go. Also, we realize that it requires an agent, as in something has to be doing the pushing or the pulling. For instance, I throw the ball. My hand is pushing on the ball. Or another example might be a rope pulling on a box. The rope is pulling on the box. Even for things like gravity, if we think about it carefully, we realize that the earth is pulling down on something. So it turns out that every force has an agent. Now, what might be a little less obvious is that we can very roughly break forces up into long-range forces and contact forces. So long-range forces are forces whose influence goes out as far as you would like, out to infinity. Gravity and the electric force fall into that category, for instance. But then we also think intuitively, well, something like friction only works if the surface that you're sliding on, if you're actually sliding on a surface, so you'd have to be in contact. With something like a throw, your hand has to be in contact, and so forth. And maybe a little less obvious, but if you think about it for a while, you come to the realization that it probably is also going to be best characterized as a mutual interaction of objects. I think we've all run into cases like, say, when you throw a particularly heavy ball, for instance, you find that you can apply a force on the ball, but apparently the ball is also applying a force on you because your hand feels really sore afterwards. Or say if you hit a ball with a bat, you can definitely tell, you're pushing on the bat, but man, that bat can push back on you, especially when you make contact with the ball. So it seems like all the interactions are mutual, and this actually turns out to be correct. But we'll get more into that in the next video series. Okay, so I'll hold off on contact forces for a bit. They almost all turn out to be some flavor of the electric force. But we'll start with the fundamental forces of nature and go from there. So, as best we currently have it modeled, there appear to be three fundamental forces of nature, but that number might be subject to revision, possibly downward. But more on that as we go on. So I'll start with the weakest of the fundamental forces of nature first, gravity. This is a force that we will be considering in this class. It's got an infinite range. As in every object in the universe gravitationally interacts with every other object in the universe. Now, the big puzzle about gravity is that compared to the other fundamental forces of nature, it is extremely weak. If the strongest of the forces of nature were, say, given an arbitrary rating of 1, some of the other forces would be at like 0.01, 0.001, something like that. And then gravity is not even a billionth as strong, not even a trillionth as strong, not even a quadrillionth as strong as those other forces. It turns out that because of various mechanisms, over long scales, like say between planets or a planet and a physicist who's sitting on the surface of the planet or something like that, over long scales it's significant because it turns out to be the only one left standing. The others all have ways of canceling themselves out, and gravity does not. But it is an open research question as to why it is that gravity is so weak compared to the other forces of nature. Okay, so within that, so then that's gravity for the moment. So let's go take a look at the electroweak force. It is a heck of a, despite the name having weak in it, it is a heck of a lot stronger than gravity. And I'm not going to really get into the electroweak force per se. Most of the time, it acts as if it were two totally different forces. One is called the weak nuclear force. And yes, that does imply the existence of a strong nuclear force. We'll be back to that. It is very short-ranged, as in the range of the force doesn't even extend across a nucleus. And it controls certain nuclear decays. That's what it's most famous for. You may have encountered beta decay if you've done a unit on radiochemistry in a chemistry course. That's controlled by the weak nuclear force. The other aspect of the electroweak force is the electromagnetic force. And it has an infinite range. It's fairly strong. Still certainly vastly stronger than gravity. More on that in a second. It is significant over, I'd say, our medium scales. This is because even though it is infinite range, there are both positive and negative electric charges. So if you put a whole bunch of positive charges together in some spot, say a pile of protons, maybe throw in some neutral neutrons into the mix just for funsies, you'll end up attracting a bunch of electrons to hang out right nearby, making an atom. But what this means is once you get any reasonable distance away from the atom, and by this, whenever you say that something's big or small, you should always ask compared to what. An atom is about 10 to the negative 10 meters across, roughly. When you start getting, say, 10 to the negative 7, 10 to the negative 6 meters away from an atom, the electrons orbiting the atom appear to be at exactly the same place as the positive nucleus. And so the interactions that you would have between the positive charges and the negative charges almost, but not quite, completely cancel out. But what this means is once you get past scales that are atomic in nature, you get the strength of you get the force having been basically nearly completely canceled out. It turns out that the electric aspect of the electromagnetic force is the main driver in what are called the contact forces. So, for instance, when you are drinking your favorite beverage, what's happening is atoms in your hand and atoms in the cup are interacting with each other via the electric force. Now, this force is almost completely canceled out. It's roughly at about 100,000th or so of its full strength, just because your hand is neutral and your coffee cup is neutral, and the only reason there's any attraction at all is that you wind up getting these very slight dislocations of the electron clouds, so the cancellation is no longer perfect. But the long story short, this completely watered down, nearly completely canceled out force is allowing you to defeat an entire planet's gravity as you drink your beverage. And I've already mentioned before, we can think of the electromagnetic force as having two aspects: the electric and the magnetic forces. So there's a bit of a history here. Near the end of the 19th century, specifically around about the 1870s, as a culmination of a bunch of work where there were experimental hints that the electric and magnetic forces were two aspects of the same thing, the theoretician James Clerk Maxwell, a Scottish physicist, was able to demonstrate that the electric and magnetic forces actually were two aspects of the same thing. Most of the time they look like two different things, but in certain cases it turns out you have to look at them as a unified whole. And so thus we talk about unifying the electric and magnetic forces into the electromagnetic force. Now it turns out the same thing happened again in the 1970s. Three workers by the names of Salam, Glashaw, and Weinberg all demonstrated that the weak nuclear force and the electromagnetic force, even though they seem to be radically different kinds of forces, are actually two different aspects of the same thing. Now, most of the time you can pretend like they're different things, but in certain circumstances you have to treat it as a unified whole. Okay, hang on to that thought as I then bring in the strong nuclear force. So to finish off the fundamental forces of nature, the strongest of the forces of nature that we know about is the strong nuclear force. It's short range, although not as short as the electroweak. Basically, its range is, say, within a nucleus. Adjacent nucleons, a nucleon is a proton or a neutron. Adjacent nucleons are attracted via the strong nuclear force, and the next neighbor over will also be attracted by the strong nuclear force. But if you've got two nucleons between you and the other nucleon you're thinking about, you're actually too far away and the force doesn't interact anymore at that distance. So it's got a range on the order of about 10 to the negative 15 meters or so. It is the strongest of the forces. It is very strong. And as I've already alluded, it holds nuclei together. Now, you've heard me mention already that in the 1870s, workers figured out that these two seemingly different forces, the electric and magnetic forces, were two aspects of the same thing. And then about a century later, in the 1970s, workers were able to show that the weak nuclear force and the electromagnetic force were also two aspects of the same thing. So it's natural to wonder, are all of the forces of nature just aspects of the same thing? And the answer is a resounding maybe. We don't have any direct evidence that it is, but there are some tantalizing hints. A combination of data looking at the absolute smallest things that we can look at, elementary particles, combined with careful study of things like the expansion rate of the universe. So about literally the biggest thing that you can look at. Combining those two together, there are hints that quite possibly these three forces of nature are all aspects of the same thing. We don't have any good way of describing that, but if you've heard about, say, people working with things on ideas like, say, string theory or technicolor or things like that, these are all attempts to try to somehow come up with a unified description for all the forces of nature as an aspect of the same thing. So, like I said, there are some tantalizing experimental hints. There are some good theoretical reasons to believe it should work this way. Nobody has yet developed the model, so if there is one, so that's something to look toward for the future. But in some future point, I may be revising this to talk about the one interaction and how everything breaks out from it. Who knows? Or not. Okay, so with that aside, let's now go and take a look at the contact forces, because for the most part in this treatment, we're going to be taking a look at gravity and the contact forces. So let's get at them with the contact forces. Oops. And it turns out that basically all of these contact forces are, as I mentioned before, are bulk models of the electromagnetic force, specifically the electric aspect of it. This has to do with the fact that if you look at any typical material, you'll have, say, about a mole of atoms interacting with about a mole of atoms. And you're going to have to treat this atom on atom. So you're looking at trying to treat 10 to the 23rd atoms interacting with, in one object interacting with 10 to the 23rd atoms in another object via the electric force. The strictly correct way to do that would be to set up a system of 10 to the 23rd equations, which is completely computationally ridiculous and unfeasible. So what we wind up doing is we develop models for how these bulk interactions work in certain circumstances, and then we give them funny names. So the first of the funny names is going to be the normal force. And this one is a truly funny name. You would think that normal here would mean something like not screwed up. After all, if you look in the dictionary at the definition for normal, you see a whole bunch of entries and they all basically say not messed up. Except that when you look in the dictionary, you ever notice sometimes when you look in the dictionary, you'll see what looks like the same word, but has two separate entries. And it'll usually have like a superscript 1 and a superscript 2. And what's going on there is that those are actually different words that, as the language evolved, wound up developing identical spelling and pronunciation. But the words come from completely different origins. So it turns out normal is such a word. If you look in, say, the Oxford English Dictionary, normal 1, you go look it up, basically all the entries mean not messed up. But then there's normal 2, a totally different word that has a different set of word origins that eventually developed to sound alike and be spelled alike with normal 1. And normal 2, when you look up its definition, means perpendicular to a surface. So these are forces that are being exerted perpendicular to a surface. So we can go ahead and start to take a look at how such a thing might work. For instance, if you are sitting down right now, you may wonder how it is that you don't fall through the chair. And this is no small question, because it turns out that almost everything you see in front of you is almost completely empty space. All very, 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 only a very, very, very small volume of space is actually occupied by matter. Yet your butt seems solid enough and the chair seems solid enough. So what's going on there? Well, in part, the electric force. So let's go and take a look at your seat. So if we go take a look at your seat, it turns out that the adjacent atoms in the seat, or the adjacent molecules in the seat, are interacting with each other via the electric force. And what I'm kind of drawing here schematically is it turns out that for things like molecules in a solid, they interact with each other via the electric force in a way that can be very accurately modeled by basically pretending that they're a bunch of balls that are connected by a bunch of springs. In fact, in organic chemistry labs, when you do infrared spectroscopy, one of the things you do is you actually work out what the spring constants of each of the bonds are. So this model of treating it as a spring is pretty darn accurate. Then, of course, chemists, being the super duper accurate people that they are, then go on to also measure what they call anharmonic corrections, which is then describing, how much does it deviate from a spring. But at first blush, just treating it like a bunch of balls hooked up by a bunch of springs ain't all that bad. So what happens, say, when your rear end comes in contact with the seat? Well, there are atoms in your rear end, and electrically they start repelling the atoms in the seat. Okay. So the atoms in the seat wind up getting dislocated from their original positions, like so. So I'm drawing the new positions of the atoms like this. This will have the effect of, say, shortening these bonds here and making, say, these, have the effect of shortening these bonds here and lengthening these bonds here. There we go. Either way, the bonds want to return back to their original length. And so this bond is going to try to pull on this atom this way, but there are adjacent bonds that are keeping that from happening. And similarly, this bond is going to want to lengthen back up, trying to push the atom back up. All of this results in the seat trying to get back to its original shape. And in order to do that, it's going to have to try to push out of the way whatever's on top of it. And so you wind up exerting the normal force. And this bit is perpendicular to the surface. Now, there's also lateral interactions that can be happening with these atoms. That gets modeled by friction. So let's go take a look at friction for just a quick moment. It turns out that with friction, there's a zillion models for it, but we'll just focus on one picture of it that is correct most of the time. So if you zoom in and look super duper close at two surfaces, what you'll see is that they aren't perfectly smooth. There will be little islands of atoms jutting in and out. So right here, you can get, say, the little island of atoms that juts down, or this juts up, and there's actually a little bit of an overlap. Now, something you can try doing right now is if you take the fingers of your opposite hands and insert them in the spaces between each other. Kind of like you are folding your hands, but don't take it all the way. Now, what you should have is like a couple of, just maybe some overlap of fingers in the spaces between each other. And then if you pull on the side, you can see it's kind of hard to get it moving. But then once you get it moving, you can feel the fingers bump up against each other. And there's still a little bit of drag as the fingers bump. Well, these fingers correspond to these little islands of atoms here. So initially, the atoms are, very well, the little islands of atoms can be pretty well locked in. You can find the little features, say, that look something like this, where it'll be very hard to get them moving sideways. But once you get them moving, then you sort of get like a surfing effect happening, where say as this surface is going this way versus that surface going that way. These 2 points right here just kind of graze each other. So we call these regimes static friction and kinetic friction. So static friction is you're going to have to overcome a force to get things moving, just to get the little islands to undo the interlocking of the little islands of atoms on the surfaces. And then kinetic is you're still going to be getting a bit of a dissipative force as things move along, as the little islands graze off against each other. So the force of friction, turns out again, it is the electric force, and it will always be parallel to the surfaces involved. Okay. We can go ahead and continue our little trip here. We can go and take a look, say, at tension or a spring force. These are related, but not quite the same. So with tension, it's like a one-dimensional version of what we were already looking at with the normal force. Let's say you have a rod or something like that, and you stretch the rod. In order to stretch the rod, you're going to have to stretch every single bond in the rod. And those bonds are going to try to return back to their original length. And so they will wind up trying to drag whatever the rod is attached to, so there will be forces due to tension being exerted by the rod on things out over here somewhere. Similarly, with tension, and this also works the same way with a spring. But with the spring, you've also got the possibility that you can compress it and make the bonds shorter, and as a result, they'll try to return back to its original length, pushing things out of the way. With tension, like with a string or something like that, though, that isn't going to happen. Because of the nature of the bonds you have there, the bonds can stay the same length, but they just don't stay in a line anymore. So this is the old thing about you can't push on a string, and yes, don't talk to me about a string that's been in a puddle in the wintertime. Because then we're back to a spring force. Okay. Also, just to kind of finish this out, a couple that are less obvious are going to be drag and thrust, which again are basically the same thing. The only difference is the direction of them. So let's go take a look at drag first. So with drag, I'm sure at some point when you were a kid, you rolled down the window of the car and you stuck your hand out, and you felt the air blowing on your hand. Well, that is literally what is happening. So say you got an object here, you're trying to move it through the air. What will happen is you will literally collide with the air molecules here. Those air molecules will have to bounce off. Now, when they bounce off, if you think about it here, this means that the object, say your hand, had to exert a force on the air molecules. But we also know that interactions are mutual, so that means the air molecules also wound up exerting a force on your hand. So say if your hand was moving this way through the air, your hand will feel a force of drag that way. Thrust is also pretty much the same thing. It's drag, but kind of backwards. So let's say you go look at a rocket motor. So yes, you are actually doing some rocket science here. By the way, rocket science is actually very straightforward. What is very, very challenging indeed is rocket engineering. Those people are real rock stars. It is really hard to build a rocket that doesn't blow up. In fact, the old joke is, what is the difference between a rocket and a bomb? 2.5 minutes. Because that's about the time it takes for you to get to expend the first stage of a rocket. So anyway, let's go look at a rocket motor here. Or this could also be a jet exhaust bell, but it's easier to think about a rocket motor. So with a rocket motor, what happens is you get fuel and oxidizer both coming in, and they somehow got ignited. One of the usual ways of doing this is you basically start a little starter fire use some stuff called T-tab to get the fire going. But then fuel and oxidizer get together and they very, very violently combust. And so now what's going to happen is molecules of the exhaust gas are going to collide everywhere with the bell of the rocket. And if you've shaped your rocket bell correctly, all of those exhaust molecules wind up bouncing straight down. So this means on net, the exhaust bell of the rocket motor was pushing down on the on the exhaust molecules, which means in turn, the exhaust molecules had to push up on the bell of the rocket, and so you get a thrust force, which I usually just write F sub T because it's a lot less common than a tension, making the rocket go up against gravity. Okay, so in the next video here, we will talk about how to identify forces and represent them in diagrams. Catch you in the next one.